All right, happy Friday. As I mentioned yesterday, we have our ICPC prep event happening here tomorrow. I'll be here at 8, registration starts at 9, but if you're interested in some practice programming problems in a competition setting in groups of 3, it is preparation for an event in November. That would be great to throw on your resume. So if you are around and available, you would be great if you could register to let us know how many people are going to show up so that we can plan. I think Jane Noonan is ordering pizza today for that for the middle of the day. There are also gift card prizes, I think, for the top placing team or two. It's worth it. Beyond that, we are in the middle of talking about NP completeness. We were introducing our first NP complete problem yesterday, and we mentioned that if we're adding our very first problem to the NP complete set of problems, that we need to fully prove that this problem is in the set NP complete. That means we can't reduce it to another NP complete problem. We have to show that it's at least as difficult as every other problem that is in NP, and that it is what we call NP hard, which if I go back to that, one slide, 2 slides ago, 3 slides ago, some number of slides ago. That didn't go well. There we go. No, and NP hard is somewhere. We're gonna find it.
Why not try to use the control F?
I like to think that I can scroll and read this tiny font on my screen, but that is a good point. Yeah, there it is. All right. I guess we've gotten past that. So we were in the process of talking about circuit satisfiability, and we talked about how an NP hard problem is one that says that every language in NP is reducible in polynomial time to the target problem. So if it's NP hard, that means every single problem that has a non-deterministic polynomial time verification algorithm is reducible to that problem in polynomial time. So I want to make sure that we're all on the same page diving into this. We had our example, we looked at circuit satisfiability, which was the concept of saying, given that we have a circuit, we want to be able to find the input wires that lead to the output wire being 1. And if we could do this, we found that we could do some pretty cool things in electrical engineering. Like we could take out a suboptimal subcircuit that has an output wire of 0. If we could show that there is no set of logic gates, or sorry, set of input wires that with those logic gates produce the output wire of 1, then it's an unnecessary subcircuit. If we could do that, we can optimize circuit design. The joke that I made is we would take electrical engineering jobs the same way that AI is taking our jobs. We just propagate the problem to the next major. But as cool as that would be, right now we don't have any clue as to whether P equals NP or not. My guess is that it's not equal, but there is no proof out there that P equals NP or that P is not equal to NP. So we have to do what we can do in the meantime, which is add problems to this class called NP complete. So let's go back into that. We found that this circuit has a solution. This circuit is not satisfiable. There is no such set of inputs that lead to the output wire being 1. And so we encoded this problem with a graph. We could say that each of the logic gates is a vertex, and each of the wires between those are edges. We found that the encoding was polynomial with respect to the number of gates. which was great. That's what we need in order to be able to represent the problem and hope to add it to NP complete. We need to represent it in polynomial time. If the worst we can do there, or the best we can do is exponential, then there's no hope that we can find a polynomial time solution to the problem, because just representing the problem would take exponential time, and that's not good. So we can represent it in polynomial time. Down that subcircuits. And then we said there are two steps for proving something is NP complete. We have to prove that it is in NP, that it is verifiable in polynomial time. The other way that I explained this was using infinite parallelism. We could solve the problem in polynomial time. If we had an unlimited number of threads, we could just fork children all day. That sounds terrible. And we also have to prove that the algorithm is NP hard. And if we can show that, then we can add our first problem to NP complete. But it turns out that this process is way harder than those two steps made it sound. So let's go through the logic of trying to prove these two components of this problem. So we first need to prove that it's in NP by showing or inventing a polynomial time verification algorithm. You can think of this as, I tell you what the input wires are that satisfy the circuit, and you need to tell me whether that is true or false. You can do that, that's a verification algorithm. Or you could say, I don't tell you the solution, but instead we utilize infinite parallelism, where we have a number of child processes that are equivalent to every possible combination of values of those input wires. And we said that there were 2 to the third in the prior example. Since there are 3 input wires, there are an exponential number of input wires, so we need an exponential number of child processes. If we have that, then we can solve each of them in polynomial time. Solve all of them due to that infinite parallelism. But infinite parallelism is not feasible. With our modern computing, we would need infinite compute power to be able to do that. But it's one way to visualize it based on material that you may have seen before. So we need to encode the circuit as a graph, converting that into binary. So you imagine you have an input binary string that represents a unique graph, that represents a unique Boolean circuit. And we need some assignment of those input wires. So we're going to loop the following process until the value of the output wire is known. For each gate with all inputs that have known values, we're going to calculate the output and then pass along that value along the output wire. And that's it. You just continue to loop that until we have the output wire of the entire circuit. When we do that, if the output is 1, we can output true. The circuit is satisfiable. And otherwise, we will output 0. There is no satisfiable combination of inputs that lead to the output being 1. So we need to rely on non-determinism to make sure that we have the correct assignment here in this process. So you can either assume that it's given to you, you always make the right selection, or we're using infinite parallelism. The 3 different ways that I like to think of non-determinism. Whatever works for you. They're all intellectually equivalent. So step 2, this one is the painful step. We need to prove that circuit satisfiability is NP hard. So to start this process, we will just set it up. We're going to say let L be any language in NP. And when I use the term language here, I'm just referring to a problem, really. So circuit satisfiability is a language. We need to compute a function to map every binary string that is the representation of the graph to a circuit such that if X is satisfiable, like if this binary string is in the language that's associated with that satisfiability, then C is a member of the circuit satisfiability problem. So we're defining a language, a set of strings that represent, based on our encoding, problems that map to those that are satisfiable. in their circuit design. Does that make sense?
We just find it from circuit is satisfiable.
Yeah, so we're making this mapping between binary being accepted in a language. A language is just a set of strings that are accepted or rejected. So maybe a list of English words that are nouns, that is a set. And the language describing that would accept if the word passed in is an English noun and reject if it is not. That's the language of English nouns. The language of English is all words that are recognized in the English dictionary. If we pass in a word that is found in the dictionary, we would output true, else we would output false. So just think of a language like that, except now instead of characters, we have bits. There are going to be strings of ones and zeros, and if we interpret those ones and zeros as an encoding of a graph, we want to define a mapping between the language of strings that are in this language with this idea of a circuit, that when we convert that circuit into its binary representation, the circuit is satisfiable, it's accepted in that language.
Yeah, it does.
That's why it's a prerequisite to the class.
That makes sense. Oh, can you go back one slide just to make sure I can think of everything? Because I did
Absolutely.
not get to write it all down. I have a feeling I might need those steps for the next, like, 20 minutes at least. Thank you.
So we want to compute that function that does that mapping. So since we know that the language is in NP, we know that there also is an algorithm that verifies it in polynomial time. So we can break down the steps of that algorithm. Instead of inventing the algorithm, we're just going to say that algorithm is a sequence of steps. That's true of every algorithm in existence. It's just a sequence of steps that define the translation from inputs to outputs from this f of x to this circuit. Oops.
There's like a defined set of steps, you know.
Right. Here are going to be those steps. We don't know exactly what's happening in each of these steps, but we can say that the algorithm is defined as such. So in each of these steps, what's happening is in the longer vertical steps here, let me zoom in on one of these so those of us remotely can see it a little bit better. This represents the state of your hardware. So think of this like as you're debugging a program, a snapshot of your variables, a snapshot of your internal representation. This is the snapshot of what's stored. And then M is the operation, what the CPU and or GPU are doing to handle those calculations. Really, it's just going to be the CPU in this case, but we're converting the internal representation at step 1 before we take a single step to the internal representation at step 2. This is clicking the forward button on your debugger. We make some calculation on this and get to the next step. Some calculation on that to get to the next step. Some calculation on that to get to the next step. And these are the internal components that we care about. There's the algorithm that we're running. Somewhere that algorithm's process is defined. So we're looking up sequence of steps and then executing those sequence of steps. There's a program counter that we need to know how many steps we are into the program, what line is currently being executed. There's the auxiliary machine state. That is just the snapshot of the internal variables and representations. We have our input and we have our working storage. I'll talk about what Y is here in a second. But at the very end of this, if I zoom in on the very bottom, somewhere in the working storage, that's just somewhere on your hard drive, somewhere in your program, probably in the program's RAM, but somewhere in your RAM, when we get done with this, there's going to be either a 0 or 1 as to whether that circuit is satisfiable or not. And we're going to look at that bit, or I guess if it's an integer, that 4 or 8 bytes, to determine whether the circuit was satisfiable or not, whether the string was in the language or not. So this would be the translation algorithm that takes as input the binary representation and outputs whether the associated circuit that represents is satisfiable or not. So that's that translation f of x that we're looking for. I'll let you take a look at that and or read the figure notation down here from the book if you would like. But are there any questions about what that represents? This is just what the computer would do as part of that, breaking it down into those sequence of steps, giving the necessary information to get started, the necessary information at each one of those steps to eventually derive the solution. Questions on that? So, yeah, as I mentioned, M implements the computer hardware. So this is, we're really doing this theoretically. Instead of running this on a machine, we're theoretically thinking about running this on a machine so that we can to do that. X is the input. So X is the input, and Y is this certificate that is telling us what the, since this is non-deterministically polynomial, it's telling us what the associated inputs are supposed to be. So as we do this, our reduction algorithm that we're going to use to analyze this has to take the input, compute the circuit that is satisfiable. So we need to know what the circuit is. We want to reduce this problem of determining this language and determine what is the circuit that is being produced here. We want to be able to at least determine that. So we need to compute a circuit that is satisfiable, meaning its output is 1, if it only exists, if there exists a certificate such that when we pass in all of this, the input and the certificate, that we get the output that is 1. If we do that, then there exists a circuit that represents this process that is satisfiable. If there is no such certificate, no such Y, such that our output is 1, then the circuit that this represents is not satisfiable. So we're creating the mapping between those problems, and we're emulating this process on a piece of hardware. We're not actually running it, we're just defining what the process would be such that it is possible to run it on a computer. By taking the idea of what a computer does and theoretically setting up the problem so that it could be run on a computer.
Really abstract pseudocode.
Yes, a very abstract pseudocode. I actually love that as a way of thinking about it or describing it. So everything about that initial state is constant, save for the certificate. So we're looking for all such inputs such that if there is some input that validates this, that creates that circuit or is satisfiable, then we can conclude yes. You can think of Y as every possible sequence of inputs. The X input is not the problem's input. That input is the binary representing the layout of the circuit. And then Y is the potential input of the values of the input on the wires. So we're going to say, does there exist such a Y, such that we can solve the problem? If we go all the way back to the circuit that I asked you to determine if it was satisfiable or not, when you tried every possible set of inputs to do that, we're just saying for whichever input does satisfy the circuit, that would be the Y that we do that produces the output that is 1. How are we doing? Questions or clarifications? Or general confusions? This is the most abstract thing we're going to do in here. It's very abstract. So, assuming there are no questions, we have to prove 2 properties about this reduction algorithm. So remember that according to this, F is going to take the input that is the graph, computing the circuit that is satisfiable. So we need to prove that the conversion between the graph and the circuit has a couple of properties. For one, this just shows that it's possible to convert between the two. But now we need to show that that conversion is fast. It's polynomial time. So I guess we need to show that one, it actually correctly computes that reduction function, and two, that it's efficient. So if a certificate exists such that when we run the algorithm on it, then C is satisfiable, we can show that directly. We can also go the other way. So this is a biconditional. We need to show that suppose that we have a circuit that is satisfiable. If there is, then there exists a set of input wire values such that when we pass that set of inputs through the circuit, then the output to that circuit is 1. So that's both directions of converting between what the reduction function needs to do. So it is doing what it needs to do. That's part one of the proof. And the second is that we need that reduction algorithm to run in polynomial time. Because if the reduction algorithm runs in exponential time, then this is not in necessarily, we can't verify it and reduce it and convert between it in polynomial time. So the number of bits to represent a configuration, we already showed this, is polynomial with respect to the input size. The program has a constant size. There are a number of instructions. The number of instructions don't vary depending on anything, save for the input size, that is the size of the graph, the number of gates in the circuit. So we will say that the length of that input, the number of gates in the circuit, is n. So the length of y, the number of input wires, has to be polynomial with respect to the number of gates, because we can't have a bunch of wires here that go and do nothing. They have to feed into some subset of those gates. And each of those gates only takes so many parameters. You have an AND gate or an OR gate, you can only take in, like an AND is only going to take in some number of those existing wires and convert them into one. So because the problem is in NP, because we can validate it in polynomial time, we have to know that the length of the number of input wires is also polynomial with respect to that. The algorithm runs for at most a polynomial number of steps or configurations. This makes sense. In each step, we're solving some number of gates. We're taking the inputs for some number of gates and converting that into some number of outputs for those gates. Once we're done, we don't go back to those gates again. So that allows us to conclude that the algorithm must run in a polynomial number of steps. You also know the amount of storage required by the algorithm is polynomial. Since there are n gates, then the amount of storage that we need to represent the algorithm, the conversion process, that's polynomial. And from there, we can conclude that the circuit that implements this hardware is polynomial based on the configuration size, which is also polynomial. And finally, we have a polynomial number of copies of the machine doing instructions, because that's if the algorithm has that many steps, then the machine is implementing that many steps. So that's also polynomial. So all of those are needed to be done in order to show that this entire process has polynomial time representation in all of those elements. So the entirety of everything on the last slide, the width of everything and the depth of everything, is polynomial. We can finally conclude from there that circuit satisfiability is at least as hard as any language in NP, meaning that we could now take any other NP language and convert that into circuit satisfiability. That doesn't mean everything else in NP complete, it just means everything in NP. There is a polynomial time conversion algorithm between any other algorithm that is in NP and circuit satisfiability. So Since circuit satisfiability now belongs to NP, we also proved that, we can conclude that it's NP complete. Really, all we've done here is show that it's NP hard. And if we can reduce other NP problems to this, we can add them to NP complete as well. We just basically want to be able to say that even if we can't come up with a polynomial time deterministic solution to something, that we can come up with a non-deterministic polynomial time solution to it. I look like I've confused people. What can I find another way to explain? Clarify?
Don't worry about me, I'm just tired.
I feel like I just need to take like a long look at the notes and just like really think about it. Wait.
That's also fair. The book goes over this in a bit more detail. It's not necessarily more understandable detail, but yeah, this process is you need to stare at it for a while and draw the conclusions between the pieces to be able to understand what's happening here. But it's not more complicated than what we run or we ask a computer to run when we write a program. And verify that the programs that we write are polynomial time. It's just that we're doing a conversion algorithm. We're converting one problem into another. Luckily, future NP completeness proofs are not quite this difficult because instead of having to reduce it to every problem in NP with that F, that we can reduce it strictly to a single target problem. We just need to take one problem, another problem, and define the connection between them, not a one to an entire class of algorithms. Is there a way to use an example to make this somewhat less abstract? The first one that we add to NP complete, there is no way to make it less abstract, but I think we go through a fairly similar process to actually add something else to NP complete. And so I think that might help. And that is what we are doing next, because I recognize this isn't the end state here. This was what we need to do to add our first problem to this language class NP complete.
We use this as like the base for solving other problems.
Yeah, now we can reduce other problems to circuit satisfiability, and we could add other problems to this language class of if we could find an efficient deterministic solution to this problem, we could also find an efficient deterministic solution to the other problem. It becomes a big if-then that we're going to start adding to a graph.
Like induction.
Yeah.
Like if I could prove that K was their first, prove that K plus one is there based on.
Yeah, kind of the conversion of the problem at size K to the problem at size K plus one. It's just that in induction, you can repeat that process to get an arbitrary number of results, and we're really just getting one result out of this. We're defining one translation from one to another. Let's look at another problem and try to reduce it to this one to give a little bit more of an example. So I recognize that that's probably the hardest thing I'm throwing at you in here. And you don't need to know or be able to reproduce this exact process. The important process is the reduction process that we're about to go through, where you're converting one problem into one problem and not one problem into an entire class of problems, where we can take an arbitrary NP problem and say, well, I could convert that into this to show that there's a non-deterministic conversion. We want to show that there's now a deterministic conversion between algorithms. Because the Y part of the last, back to it. There were options here as to what the Y could be. We had to use non-determinism as part of this linking. That proved that it's as hard as other problems in NP. We want to now link in the future. We don't have to say there's going to be an arbitrary Y. We can say for each Y, what is the associated conversion. And that is significantly easier. Okay, we've gone through the pain, we've proven that there is a single NP-complete algorithm. So let's try adding another problem to it. We're gonna pick something that's very close to circuit satisfiability to do that.
Very close, eh?
We want it to be intellectually very close to it, logically very close to it, intuitively very close to it. So it can now be the end state of a reduction from an unseen problem to this problem that allows us to add it to this class of if we could solve one of them efficiently, we can solve all of them efficiently. So if we could convert some unknown problem into circuit satisfiability and polynomial time, then we can say if we can solve one of those problems efficiently, we can solve the other one efficiently. So steps to this, we just want to prove that the language that we are now converting an unknown problem, that's what we're going to call that a language. We're going to prove that is in NP. We're going to prove that it's NP hard, just like we already did. But to prove that it's NP hard, instead of going through everything that is in NP, we can just now select a known NP complete language and describe an algorithm computing the mapping between that. Every instance of the language we know is in NP complete and an instance of a problem that is the language that we're trying to add to it. Then we prove that F satisfies X is in L if and only if F of X, sorry, it's L prime. X is in L prime if and only if F of X is in L for all possible inputs X. Does that make sense as a statement? A couple of nods, a lot of blank stares. Excellent.
Think so.
That's what really defines that conversion. If I have a way of converting all integers into floats, right? There's a good way to do that. I can take the integer 3 and convert it into the float 3.0. So I just need to be able to say X is in L prime. That says that so we're using the target here. The known NP complete language might be the integers. We want to prove that there's a mapping between the integers and the floats, or at least some of the floats. We would say X is in L prime if and only if F of X is in L for all X. That's not going to be true for integers to floats because there exists a float that can't be converted into an integer. We can take the floor of that and do integer division, or just kind of floor and get there, but we could do that. And we just have to prove that the algorithm computing that function runs in polynomial time. So it's the same kinds of steps, but instead of an arbitrary number of endpoints, there's a single endpoint. So the problem we're going to use to do this is Boolean formula satisfiability. This is the SAT problem. So we solved circuit SAT, and now we're going to solve SAT. This was actually the first problem that was proven to be NP complete, but we're going to use it as the end goal. So we have a Boolean formula. We have n Boolean variables. Each of them are either true or false. Then we're going to have a formula that consists of ands, ors, nots, implications, and bidirectionals, or biconditionals. We can also have parentheses to override our default order of operations. The question I have is, how could we encode a Boolean formula? Any thoughts on encoding a Boolean formula? You have one of these logical formulas and you want to convert it into binary in some capacity. How could you do that?
struggle with most of it.
It's a bit of a challenge. So we have some number of characters here, right?
Yeah,
There's only a limited number of characters that we could possibly see. We could see x sub 1 through x sub n. We could see any of the logical operations, the and, the or, the not, the implication, the biconditional, and a left parenthesis and a right parenthesis.
well,
We've actually done something in here that would help with this.
would be that circuit problem we did with the gates earlier,
A good idea. For that, we used a graph.
right?
Could we envision a Boolean formula as a graph? Does that make sense? Not easily?
Yeah. I was gonna say, I'm pretty sure the answer is no.
What about Huffman codes?
Oh, yeah.
That's what I was thinking. I just
I did not, I regret not practicing that enough for the last exam.
don't know how you would, how could you, I don't know.
You have some set of Boolean formulas out there, and you want to figure out approximately how common are each of these. You could devise a Huffman tree that converts each one of those into some number of zeros and ones that are understandable between. And we could map that into a long string that is a binary string of zeros and ones that we could then parse into the exact Boolean formula in its representation. So this was just an idea that I had. This didn't come from the book, but regardless of how we encode it, we just need to find some kind of encoding. We need to make sure that the length of that encoding is polynomial, and it will be polynomial in n plus m. N is the number of characters here, m is the number of Boolean operations that you have. Thinking about solving this in a brute force fashion. How could we brute force determine whether a Boolean formula is satisfiable or not?
Operation, and keep track of whether it's like a zero whole wing.
Yeah, we're going to take x sub 1 through x sub n and assign every possible combination of ones and zeros to that, just like we did with the input wires on the circuit satisfiability problem. So we check all 2 to the n assignments. Each one of those is going to take polynomial time. So we end up with something that is exponential. This makes sense. So it's not practical to go through an exponential number of polynomial time verifications. So it makes sense this problem is NP hard. You can start to see the link between the circuit satisfiability and this problem. The inputs to the wires are the same as the inputs to the Boolean variables. The output to the circuit, whether the circuit is satisfiable, is the same as whether this Boolean formula is satisfiable. We're still outputting a 0 or a 1. Is there some allocation of these variables in some way that allows the output of this expression to be 1? So it's a very similar type of problem.
Basically, any problem that just resulted in steps that would, you could say that it's similar to the circuit one.
Yeah, that's what we're going to go through and formalize to basically say, could we convert a Boolean formula into a circuit? And basically say the Boolean formula is satisfiable if and only if the circuit that is equivalent to it is satisfied. We just need a one-to-one mapping of Boolean formula to circuit. So that's what we're going to try to prove the mapping exists of. If we convert an arbitrary Boolean formula into an equivalent Boolean circuit, such that the Boolean formula is satisfiable if and only if the Boolean circuit is satisfied. So step 1 of this is we have to prove that it's an NP, which means we need a polynomial time verification algorithm for it. So you can assume that someone who has already solved this problem tells you that exact answer. Or that you have a machine capable of infinite parallelism, and you can try all of these exponential number of assignments in parallel at the same time. Since each one takes polynomial time, the entire thing would take polynomial time if we have that level of parallelism. So we already showed that evaluating a Boolean expression takes polynomial time because of the Boolean circuit. So let's show that it's NP hard, and we can show that it's NP hard by reducing it from circuit satisfiability. We're going to take our last problem and invent a conversion algorithm between those two problems. Let's look at a naive approach. We're going to start at the end of the circuit. We know that the circuit has output either 1 or 0. And we could recursively then say, well, if the output to this circuit is 1, what do the inputs to that circuit need to be? We can take that and recursively move backwards, 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 and attempt to solve each of those to be able to get some kind of input wire for that. There's an issue with this. Can anyone think of the issue with that approach?
I have a, it is recursive, but it is more of a brute force approach to go through all of it, which is, it takes a really long time.
Sometimes.
More than 40.
Yeah.
We could handle it recursively, I think, and be able to deal with it. So stack overflow isn't the issue. Would you guess though? What is something that we needed to be true about this conversion process? There was some requirement.
To be prove, we need to prove that it's polynomial time.
Yes.
And this is taking much longer than that.
Potentially. What would the setup of the problem be such that this conversion is not polynomial time? We're treating this like it would be a tree, where we can take the input from one and calculate the output from one, calculate the input of the other. So this creates the ability for there to be shared subcircuits, which means that we can't answer them in parallel. There's going to be an order to them that we need to solve something, an entire subproblem before we can move forward on the next one. And then we might have to resolve that and resolve that in ways that even dynamic programming won't help us. So the output wire can branch, which causes the Boolean formula that's based on it to grow exponentially. There's an example of this in the book that makes this a little bit clearer.
You always have split two.
Yeah, the outputs can split. Whenever we split a wire into two wires, we have to have solved that subcircuit in order to be able to map it. We have to have that output being the same so that we can look at the input, which means we have to solve the same problem multiple times to validate and verify that the input can be the same. The output can be the same going into the input. So there is a better approach to this. We should label each wire. Rather than labeling and thinking about this from gate to gate, let's think about each wire. We want to make a clause out of each gate that uses bidirectional implication. Let's take a look at this on the next slide, and it looks really nice. So this gate has output 1 if and only if the inputs something. And we can recursively expand that in a way that works. So let's see this. So how long does it take to produce the formula from this circuit?
every wire.
So X10 is on if and only if X4 and not X3. And X5 if and only if X1 or X2.
Okay, X6, if and only if not X4. And X7, if X1 and X2 and X4. It's a mouthful. And X8. 5, 4. I should probably not put my whole office, sorry.
So we're just relaying the gates in their own expression here, but we're saying that every output from that has to be satisfied, as well as the output wire has to be one. So we have a new expression here. We have a Boolean expression here for the circuit. Does it make sense how each one of these sub-expressions is the input and output to each one of these gates? Based on the wires that are input and output? So how long does it take if we were looking at this circuit to produce this formula?
Would it take polynomial time? I'm wrong.
That's a good question. There are n gates.
Yeah.
How many gates are there in this case?
10.
We have 7 total gates.
Oh, yeah, sorry.
10 total wires, but 7 total
I
gates.
saw it.
And we have 7 total expressions here, with an 8th one being the output wire.
Okay.
So that is polynomial. So we can convert a circuit into an expression that relates the circuit in polynomial time. The next question we need to ask is the circuit satisfiable if and only if the Boolean expression is satisfiable?
Yes.
Kind of by definition, almost. And it turns out this is all we need to be able to show the reduction, is that we've come up with the translation function that goes from one to the other. And we're done at that point. We've shown the function that does that. We don't need to go through all of the verification that we did before, proving how this runs on a machine, every step of what the inputs and outputs are. All of that was to just add the very first problem to NP complete. All we need to do to add a problem to NP complete now is to find this mapping from one problem to another problem, such that for any circuit, you can come up with an associated Boolean formula that is equivalent, that is satisfiable if and only if the circuit is, the formula is. And this process will always work, and it'll be fine in polynomial time. You look at each gate as a separate entity. But you're looking at it based on the wires and not on the gates. If you focus on the gates, you end up with an exponential time issue because of how the wires can branch between gates. But if you focus on the wires as the variable, then we can come up with a polynomial time conversion that looks at the wires. And a Boolean formula of the wires based on the gates creates this expression. So this is the moment of brilliance that allows us to be able to reduce this problem.
You have a definition. Trying to show that it could be some form to show that it's.
Yeah. This is equivalent to that because we can find the mapping between them. That was a mouthful. This class was a lot.
Yeah.
Question?
So we have to be able to find the mapping, and the mapping has to be in polynomial time.
Yes. Yeah, we have to be able to, given a circuit, produce this in polynomial time. Which we can show because there is only one of these expressions for each gate. We can go gate by gate and say that is this. X10, the output, is true if and only if all of the inputs are true, because it's an AND gate. X9, the output is going to be true if and only if at least one of the inputs is true, because it's an OR gate.
That makes sense.
And you do that gate by gate, and you end up with a linking. It doesn't necessarily say whether this problem is satisfiable or not. We're not looking at that. We're looking at if this is satisfiable, then that is satisfiable. And since we can't solve this problem efficiently, now we can say if we can solve one of these two problems efficiently, now we can solve the other one efficiently. And that's the best we can do. All right, I have office hours starting now, and we'll come back to this on Tuesday with some more NP complete problems. A little bit more experience with this. I apologize for a very dense class on Friday. Not the best day to do it.
I'm worried that you're gonna work at it.